This is a video where I'm going to be introducing the ideas in Chapter 4. You should watch this video as you start reading Chapter 4, Section 4.1 in particular. The main subject of Chapter 4 is what are called forced harmonic oscillators. Forced harmonic oscillators. They come up in the harmonic oscillator equation when you've got what's called an external force. And how an external force is modeled is with a function on the right-hand side. In most applications, and in fact all the applications we're going to consider, that function will be a function of time only, not of the position or velocity or acceleration of the mass. It'll be an f of t. So that right-hand side represents external forcing, and as you read the book you'll see there's a derivation of this equation in terms of thinking about it with Newton's second law. The little f of t again represents some kind of external forcing. You've got forces that come from Hooke's law, the restoring force of the spring, that's the ky term. It's initially a negative ky term on the other side. You've got the damping force, that's proportional to the velocity, that's the by prime term, initially as a negative by prime on the other side. And then you've got this other force. The book gives you various ways to imagine how this other force might occur. For example, an opera singer and a glass, and the opera singer sings a certain note, and that, the sound waves are the external force for that glass and perhaps can shatter the glass. Here's another way you can try to visualize it. You can imagine perhaps a table, and you've got some very heavy kind of thing that's attached to the table and it's immovable, and then you've got a mass on a spring attached to that thing that's heavy and immovable on the table. You let the mass on the spring start going, and then you come over here, here's you, and you start moving this table up and down. Okay? So sometimes it's slanted. That object that's attached to the table and really heavy stays where it is, but the mass on the spring obviously can move up and down. In effect, you're changing how the force of gravity acts, and if you do this in an up-down motion, you might be able to model your up-down motion with a periodic function like a sine or a cosine, and that's another way you can imagine the external forcing coming in. Here's yet another way. I'll come over to the CD-ROM on my computer. If you go to forced mass spring, I think I showed you this way back in one of the first few videos in the course. Don't remember offhand. What you've got here is a mass on a spring. Let's get rid of the damping. That comes from the thing at the bottom. You see that thing disappeared there? Over in the lower left. When you've got damping, there's damping there. It goes away when the B is 0. That thing that was there is supposed to somehow represent, I don't know, some friction coming in. Perhaps it's a tube filled with air, whereas everything else is in a vacuum or something. And by setting B equal to 0, you make that go away. Got the spring, you've got the mass. This thing up here, this plunger type object, is supposed to represent the external forcing. It's going to push the mass up and down, though down over here and on the right, the force, that's the capital F that you see down there, that comes from that external forcing. The amplitude of that force, represented by this F, is actually set to 0 right now. So if I let this go, there should be no external forcing. That plunger at the top left should not move up and down, and it's not, and you see a periodic solution. As usual, if I add damping, by making B positive, your solutions are not periodic. They do oscillate, but there's an exponential decay, and eventually it gets to the point where you can't tell the difference between the model and no motion. Technically, there's still a tiny oscillation going on, but we can't measure any oscillation when we look at it. What if we want some external forcing now? Let's have some damping in there. I'm going to go down to the lower right here, the F slider, move it up. So I'm increasing the amplitude of my forcing. The funny looking W there, that's called an omega, is going to be a measure of the frequency or period of my oscillation. The period will be 2 pi over omega, and the frequency will be omega divided by 2 pi. So the bigger W the omega is, the faster the external forcing is going to oscillate. I'll just pick something here. Let's see what happens. Just got a little bit of damping. You've got the external forcing, which you can see is causing some strange behavior to happen. And it actually seems to be approaching some kind of steady state here. Notice in the phase plane, the solution curves are actually crossing. That doesn't violate the uniqueness theorem, because this is really a non-autonomous system. And with non-autonomous systems, where you've got a T on the right-hand side, you really should interpret the uniqueness theorem in this situation. In terms of a three-dimensional picture, you should really, in a sense, imagine a T-axis coming out of the screen. And while the solution curve can cross itself in the phase plane, the YV plane, it's opposite of the usual way here, Y on the top, V on the side, distinct solution curves will not cross in 3 dimensions if you follow the solution curve forward in time into this 3rd dimension. It will not cross itself. T has to keep going forward. And it would also not cross any other solution curves. So the uniqueness theorem still holds in that 3rd dimension. It's not violated. One real interesting phenomenon that happens, especially when the damping is 0 or very close to 0, occurs when you get the outside frequency, the external frequency, very close to what's called the natural frequency of the spring. Let's see, the natural frequency of the spring in this case should be close to 1. We'll figure out why in a later video. So if I let omega be close to 1, that should produce something interesting. I'm going to start with the initial condition close to the origin. And the oscillation gets bigger for a while. But it seems to be doing what I wasn't expecting. Let's see, maybe we need no damping at all here. Let's clear that. Make the damping 0. Let's try it again now. So it's getting bigger and bigger and bigger and bigger. We don't have any damping. Maybe I should... Okay, now it's doing what I was hoping it would do. The oscillations are getting smaller now. But then the cycle will repeat itself. We are close to something called resonance here. And if I stop this and made omega, in fact, exactly equal to 1, we would be exactly at resonance. And in this case, the solution curves keep getting bigger and bigger and bigger, but never get smaller. And in fact, you look at the spring on the left, and it looks like it's doing something that should cause it to break. It's going off the screen, okay? So this is resonance. And our main goal in Chapter 4 is to understand this phenomenon and why it occurs. And we will be able to. So how are we going to start to try to do that? Well, the first kind of example we'll do will be a situation where we'll take the external forcing to be an exponential decay. to keep things actually initially as simple as possible. With that resonance phenomenon, the external forcing would be a sine or a cosine or some combination of those. That's a little bit more complicated. So let's try to get the idea of what's going on here with a simpler example where the external forcing is exponential decay. Writing this in the standard form, we usually do to keep things simple by making the coefficient of the y double prime equal to 1. We divide everything by m, and we can write it as y double prime plus py prime plus qy equals f of t divided by m, and we'll just give that a new name. We'll call that g of t. Let's let the g of t be an exponential decay. In particular, I'm going to look at problem 10 in section 4.1, at least in the whatever edition I'm using right now, the third edition of the book. In a future class, it might be not problem 10. I don't know. We'll see. Here's what it is. Y double prime plus 7y prime plus 12y equals 3e to the negative t. If we wrote this as a system, it would look like this. Y prime equals v, v prime equals negative 12y minus 7v plus 3e to the negative t. It would be a non-autonomous system. As we saw in section 3.6, with these kinds of equations, it's actually, unless you're doing Euler's method or something, or looking at the phase plane, it's actually advantageous to avoid going to a system, to just guess solutions. And that's what we're going to do. It's not autonomous, it's also non-homogeneous. The right-hand side is non-zero. It's, in this case, a function of t. You might recall back in chapter 1 when we had first-order non-homogeneous equations that involved only first derivatives, that we used a certain technique, the method of undetermined coefficients, that involved first looking at what's called the associated homogeneous equation. The associated homogeneous equation that we get by taking the right-hand side and making it 0. It's not the same as the original equation. It's not the ultimate equation we want to solve, but it is associated. And it helps us find the solution to the original equation. Make that right-hand side 0. Now this is in the form of chapter 3, in particular section 3.6. It's quickest just to guess e to the st and solve for the values of s that are going to give us solutions. Those will be eigenvalues, in fact. The associated quadratic equation will look like that, just taking off those coefficients. And from the quadratic formula, the values of s that will work, the eigenvalues really, of the associated system, look like this. In fact, I could have just factored the original one, but it's always good to practice the quadratic formula. Negative 7 plus or minus square root of 1, which will be 1, over 2. Negative 7 minus 1 over 2 will be negative 4, and negative 7 plus 1 over 2 will be negative 3. And yeah, I could have just factored this initially as s plus 4 times s plus 3 equals 0. That's another way of seeing that. But the quadratic formula is going to be more useful in general when your roots won't necessarily be real nice numbers, which, as you've seen in some homework problems, does happen sometimes. So we've got the general solution of the scalar equation as a linear combination of e to the negative 4t and e to the negative 3t. That's the general solution, not of the original scalar equation, but rather of the associated homogeneous equation, so I'm going to call it YH, just like we did in chapter 1. So that was the first step in chapter 1. It's also the first step now. Find the general solution of the associated homogeneous equation. That's what we've just done. It's a little bit more work than in chapter 1. Chapter 1, our associated homogeneous equation typically looked like this. Y prime equals something times y, a times y, and the answer was like constant times e to the at. Here it's a bit trickier, but not too bad. Second step back in chapter 1 was to find a particular solution to the original equation. We do that again here. That was usually a bit more work back in chapter 1, and it will be a bit more work here now. Y double prime plus 7y prime plus 12y equals 3e to the negative t. We want to guess a certain solution to this. Call it yp for y particular. It always brings up the issue, what do we guess? You can use some common sense, some calculus common sense here. Your guess is going to be plugged in on the left-hand side. In a sense, this left-hand side is kind of like a linear operator. It's telling you, take your guess, find its second derivative, add 7 times its first derivative, then add 12 times the function. You're looking for a guess such that when you plug it in that linear operator, out pops the right-hand side as the output of the linear operator. Out pops 3e to the negative t. Euler's formula notwithstanding, it sounds like trig functions, cosines and sines, are probably not good guesses here. We're sort of ignoring our knowledge about complex numbers, thinking in terms of what you learned in first-year calculus. Cosines and sines don't sound like good guesses. You're going to get cosines and sines back out. E to some power sounds like a good guess. Derivatives of e to powers give you things involving e to powers. In fact, it probably should involve e to the negative t, if you're going to get an e to the negative t involved in the output. The only thing that's undetermined is the constant that might go in front of the e to the negative t. You can call the constant anything you want. The book does from time to time use different letters. I'm calling it k here. There's no guarantee here initially that this is going to work. And in fact, you will see in the book, in one of their examples, and sometimes in homework, that this thing, while it looks reasonable, actually won't quite always work. In particular, when your multiplier of the t in this exponential function also ends up being an eigenvalue of the associated system, for the associated homogeneous system. That's a situation where the guess won't work, and you'll see that you have to modify the guess by multiplying it by t. But -1, the coefficient of the t here, is not an eigenvalue. We saw the eigenvalues were -3 and -4. So it'll turn out that this guess will work, but we do need to figure out what k will be. Y prime is -k e to the negative t. Y double prime is back to y itself, k e to the negative t. Substitute it into the second order equation. Yp double prime plus 7yp prime plus 12yp. You're going to get k e to the negative t minus 7k e to the negative t plus 12k e to the negative t. And that will simplify to 6 e to the negative 6k e to the negative t. I want that to equal the right-hand side of the original non-homogeneous equation, 3e to the negative t, so I'm going to set it equal to 3e to the negative t. The only way those two things are going to be equal for all values of t is if 6k equals 3, so k is 1/2. And that does work. That will make both sides equal for all values of t. So yp equals 1/2 e to the negative t will be a particular solution, one function that solves the original non-homogeneous equation, the original forced equation. The associated homogeneous equation is sometimes called an unforced equation. But the original one here is forced. There's an external forcing function. There's an extended linearity principle, just like in chapter 1. and just like in chapter 3, although it's back to scalar functions, that says that the general solution of the original non-homogeneous equation, or forced equation, I'll use the word forced here, is a sum of YH and YP. So that gives us K1 e to the negative 4t plus K2 e to the negative 3t plus 1/2 e to the negative t. All functions that look like that are solutions of the original non-homogeneous equation, the original forced equation, no matter what K1 and K2 are. And it also turns out, conversely, that any function can be written, any function that solves that non-homogeneous equation can be written in this form. You can solve for K1 and K2 to solve any initial value problem you want. That's just some algebra. I'll let you do that as usual. I will remark that, as in section 3.6, you do need two initial values. You need an initial value of y and an initial value of y prime, or v, in order to solve for both K1 and K2. But you would find y prime, you'd plug in t equals 0 typically into both of those, at least if you're going to have nice values of K1 and K2. We're going to hope for initial value problems where t is 0. And that'll result in a system of algebraic equations that you can solve for K1 and K2. And it'll be simple at t equals 0 because e to the 0 is 1. So that'll make for relatively simple systems of equations. So this is the method. And for section 4.1, it's really not much more difficult than this, except in that one case where the multiplier of the t up here is the same as one of the eigenvalues. Again, to reemphasize, in that case, you end up multiplying by an extra t in here in your guess. It makes it a bit more messy because you have to use the product rule in addition to the chain rule when differentiating the function, and so it makes your work a bit messier. But that is what you do, and it will work out in those cases to give you the general solution and also allow you to solve initial value problems. I guess I'll wrap up this video by emphasizing one more thing that the book does emphasize in section 4.1, and that is that the associated homogeneous equation, the unforced equation that's associated with the original forced one, is like a chapter 3 type of equation. In particular, a harmonic oscillator equation from chapter 3 where the p and the q are positive. And if you recall, what happens there is, depending on the values of p and q, I guess the p could be 0 when you've got undamped harmonic oscillators. You get those situations whether it's either undamped, underdamped, critically damped, or overdamped. In all the cases except the undamped, the origin ends up being a sink, though a different kind of sink, either spiral or non-spiral. In the case where p is 0, you get a center at the origin. So if we're in the case where p is bigger than 0, it's, again, underdamped, critically damped, or overdamped, the origin is still a sink for all of those. The general solution will involve exponential decay, and therefore will go to 0 as t goes to infinity. That's still going to happen here as long as there's some damping. The YH is still, as long as the p and q are positive, going to end up giving you functions that go, a function that goes to 0 as t goes to infinity. With this particular formula, each of these three terms goes to 0 as t goes to infinity. But if I had put a forcing term on the right-hand side that grew as an exponential growth as t went to infinity, that term would not go to 0 as t goes to infinity. That's not realistic. You don't want external forcing that grows indefinitely. More realistically, in sections 4.2 and 4.3, we're going to look at situations where we have a trig function on the right-hand side for our external forcing. The yp won't grow to infinity, but it also won't decay to 0. It'll be a sine or a cosine or some combination of those. And so in the end, the upshot of that is the YH still goes to 0, but the YP doesn't. And so all solutions in the long run end up approaching the YP as t goes to infinity. And that's sometimes called the steady state solution. It's going to be the long run behavior of the system for any initial condition. We'll begin to have more fun with complex numbers in Chapter 4. In a sense, it's even more fun than in Chapter 3. So you have something to look forward to there. I like it a lot. It's strange, but when you really get it, it's kind of fun. It'll help us figure out the behavior of that steady state solution, which is not a constant function. It's not an equilibrium solution. It'll help us figure out the behavior. Using complex numbers, amazingly, will help us figure out the amplitude and the phase of that steady state solution in those sections. That's the end of this video.